Hello guys, how are you doing? I'm going to do this lecture again, hopefully until the end, because yesterday I tried to do the same structure with toothpicks and glue gun. My students laughed at me and they have reason to do that. So let's see, yesterday I built this contraption here and let's see how it goes with that. Let me change this to just the webcam, not webcam, this one. Okay, so today we're going to be dealing with zero force members for 3D. And in 2D we already covered that, but I want to review really quick. So there were two rules about zero force members in 2D, and those were very easy rules to follow. The first rule, it says that if in any particular joint you have two, and remember this is very important, two. What two? Two bars, two forces, or any combination that adds two, and they are non-collinear, both of them must be zero. So if you check this truss, this 2D truss here, and you look at the joint D and the joint A, you can see that those joints matches perfectly with this rule. You have only two bars or two bars here, and they are non-collinear, hence both of them will be zero and the actual truss will be that. In this one you don't have two, this is a pin, so you have 1, 2 plus the two reactions, that would be 4. The rule wouldn't apply to that. The reason for that is, I'm gonna try to check it. Let me see if I can do it here. Whatever you have, let me change that view because I don't like that view. Let me use this view here. If you have two, let's say that you have these two bars here, and remember these connections are pins. So whenever you are applying any force, if in any of these bars there is a force, this is going to happen. This is going to try to push it in that way, or this is going to try to push it in that way, or pull it. So there is not any possibility for any of those bars to have any force, to carry any force, because this is a hinge, this is a pin in that part. That was the first rule. Now the second rule for zero force members was also a very easy rule, and the rule was this. Now the first rule, remember, it was 2. In this rule, the rule starts if at any joint you have 3 what? 3 forces, 3 bars, or any combination that adds 3. And this is very important also, the and. 2 of them are collinear, then the one that is not collinear should be 0. If you look at that rule, the rule doesn't say one perpendicular, but if you look at this one, you have 1, 2, 3. This is a perpendicular, but you don't care about the perpendicularity. And in this one, you have also 3, 1, 2, 3. 2 of them are collinear for joint D, and 2 of them are collinear for joint C, meaning this bar AD and this bar AC must be 0 per that rule. And this is what happened there, and this is the ultimate or the final truss. If you look at this joint, you have 3, but you don't have 2 of them collinear, 2 bars and a force. If you look at this joint, you have 4, 1, 2, and the 2 reactions of the pin. That doesn't count. And if you look at this one, you have 1, 2, and 3, but the reaction from the roller is not collinear with any other ones, or they are not any of the 2 collinear. Now, how would you explain that? You can explain that with this. If you have something like that, and you have 2 bars that are collinear, I can push and pull, and they are going to counter each other out. But if I, by any chance, just push this in this direction or pull it in the other direction, what is going to happen there is that immediately, that joint will become unstable. That means that this bar here must be 0 for keeping the stability of that joint. This is the way that you can show and demonstrate those two very simple rules for zero force members in 2D. Now, we're switching to 3D. And in 3D, the rules are the same, basically. And I'm going to read the rules. You can read it there. But basically, I'm going to apply the same wording as in 2D. This rule will be the equivalent of if you have two of them. No, if you have, this actually will be the equivalent of the second theorem. That is, says if you have three in a joint and two of them are collinear, then one that is not is zero. In this case, you talk about planes, and you can say that by saying if in a particular joint, let's say joint B, all of the forces belong to a plane except one of them that doesn't belong to the plane, that will be zero. For example, if I put a plane in the back of the joint B, you can see that the force P, this bar and this column here are in the same plane, and this one here is just going out of the plane. That bar must be zero. At the same time, you could have seen this in a different way. You could see, for example, you could say that if you put a plane on the top at the joint B, this force, this bar, and that bar belong to the same plane, meaning the column should be zero. That's another way of looking at that. How can you show that? How can you demonstrate that? Well, you can demonstrate that fairly easy. If you have a joint, let's say like this joint. This is a Weir joint. But if you realize this, and this bar, all of them belong to the same plane. So if I put them flat in the plane, there is only one bar coming out of that plane. And doesn't have to be perpendicular, by the way. It can be in any inclination. But if this is the only bar going in that plane, and if I do some going out of the plane and I do summation of forces with respect to that axis, that bar has to be zero. And if I push it in this direction, because this is a joint, it's a hinge, 3D hinge is going, or a 3D ball and socket, is going to push this, and it's going to cause instability in that joint. So that's another way of demonstrating that rule. Remember, the rule is if in a plane, if you have all the forces, absolutely all the forces in one plane, except one of them, and that only one, and that goes in a different direction, in a different plane, that is a zero force member. There's another rule. A lot of people are going to tell you there are 7 rules. No, there are only 2 rules, and then you can combine these rules also with 2D. And I'm going to do it in one example that I have. The forcing member A is 0, that's what I said before. Now the second theorem is, which I don't know if we call it second theorem, because it's an application of the first rule again. But the second rule will be the equivalent in 2D of the first rule that says if in a joint you have 2 and they are non-collinear, both of them are 0, that will be the equivalent of saying this. If in a joint you have 3 and the 3 of them are not in the same plane, 2 of them of course are going to be in the same plane, because you can draw a plane between 2 lines, but there's one going out of the plane and none of the 3 of them are in the plane, all of them should be 0. That will be, once again, the equivalent of having something like this. Let me see, let me switch the view here. Whenever you have this little pyramid, I call it the pyramid, it's not, but whenever you have something like that and you have only 3, 1, 2, 3 over there, you automatically can eliminate the 3 of them. Or if you don't see it, you can say, oh, let me apply the first theorem, and I put it flat like that. When I put it flat like that, the first theorem says if all the bars or the forces fall in one plane, guess what? These 2 fall in one plane, and there is only one going out of that plane, then that will be 0. If this is 0, I can take it out, and if I take that out, if it wants to get out, then look what I have here. I have the rule for zero force members in 2D. When a joint I have 2 and nothing else, both of them are 0. So you can learn it like this and say, oh, whenever I have that little pyramid over there and nothing else, if I have a force here, that doesn't apply. That wouldn't apply. I could try to see if the force lay in the same plane of the other two and apply the first theorem, but you cannot eliminate the three of them. However, if you have only three, you can eliminate that perfectly. And those are the basic two theorems, which is only one, but let's call it two, because I don't want to hurt people's feelings, for zero force members in 3D. Now, let me do a disclaimer here. This problem is not a real structure. That structure is a weird structure. This is just a problem that I'm using to demonstrate zero force members, and let me tell you, there's tons of zero force members there. So hopefully at the end of this, you will be able to identify zero force members in 3D. Let's start. This is the structure that I just did with springs and magnets and kinetics. So let's see if it comes handy or not, but it's the same structure that we have here. So I'm going to try to show these side by side, like this, and see if we can see it. I'm gonna start moving this camera around, so don't get dizzy. I know some people get dizzy. So identify all zero force members. Okay, let's start with the first one. And it doesn't have to be that joint, but let's say that we start with the joint L. Now, if I put a plane in the back of the joint L, you can see that this force here, this force here, and this force here, all of them fall in the same plane, meaning LK must be 0. And that will be the first theorem. Let me show you, or try to show you. I don't know how this is gonna end, but I'm going to keep it no matter what, and all the bloopers will be there. That is the joint that we are discussing here. So if you see that joint, this bar or this force is a force. I treat it like a bar, but it's a force. This force, this bar, which is LG, and this bar, which is LM, all of them go into the same plane. If you see it from here, I can put a plane in the back over there. Let me see, over there, and you can see that the three bars that I mentioned are in the same plane, and the only bar coming out of the plane will be this bar here, meaning that is a zero force member. As I said, you don't have to start like that, because if you do it with this plane here and you look at the joint K like that, you can look at the joint K like that, you could see that this member also is the only one that don't belong to the plane that I place in the back. So if that is the case, that will be also a zero force member. But let me try to keep going and see what happened here. I hope that this is not gonna be destroyed completely. So the first thing that we did is that this bar is a zero force member, and I'm going to take it out, hopefully without breaking anything of that structure. Now our structure, if you look at the structure from this side, doesn't have that member. I just put that bar, that black bar over there to keep the structure stable, and that's it. But that bar is not there anymore. Okay, keep going. When I say keep going, I didn't mean for the camera to pause, but keep going. Okay, so KL is 0, take KL out of the equation. Now, when I say that you can combine, that's what I mean by that. Look what happened with the joint L. If you look at the joint L, this is what happened. You have 1, 2, 3, 1, 2, 3. Two of them are collinear, and that tells you that this bar here, LM, must be 0. And this is a rule for 2D, but because all of them fall in the same plane, I can apply 2D there, because they are 2D for that purpose. In this part here, you see, this is the joint that I was referring to. Two collinear. This is a little bit tilted, but it's fabrication defects. Disclaimer. So this bar must be 0, and that's what we are eliminating there. LM equals 0. So let me try to, I don't guarantee that this is gonna hold. Hopefully it will hold. out of there. Okay, now that bar is not in place anymore. Where else can we go? Joint K. If you look at the joint K, this is the joint K. If you look at the joint K, look at over there in the PowerPoint, you can apply the same principle of the plane, and you say, I'm gonna put a plane in this part. So if I put a plane in this part, from this angle here, you see, joint K, I put a plane here. These two forces, these two bars, go in the same plane. However, Kj is coming out of the plane, and I could eliminate that bar according to the first theorem. Now, there's another trick here. If you look at these three bars, those three bars over there are these. That's that little pyramid over there. Okay, this is 90 degree. Okay, let me put it 90 degree. So what you have there basically is something like this. Two of the bar and one perpendicular. If these two go in the same plane, these go out, I can eliminate that. Or I can just say, oh, look at that. I can eliminate the three of them at once. I didn't do it like that in the PowerPoint, so I'm going to follow the same method that I use in the PowerPoint for that. What I say is Kj is 0 because of that, and Kj is 0, so let me try to take Kj out of here. There you go, Kj. No more scissors, guy, because I was cutting it with scissors in class. Now, Kj is 0. The bar here disappeared, or I made it disappear for clarity purposes. And now, look what happened with the joint K. If you look at the joint K, once again, this is a rule for 2D zero force members. So I can come here, I can try to move these to the side so to see if you can see it. You see there? This joint here is a joint, only two bars coming to that joint. What that means is that both of them must be 0. Most of them must be 0. And they should disappear from there. Now this is gonna be interesting because I don't know if I'm gonna be able to do that here, but I will definitely try to, if you promise not to laugh too hard with these faults. That was this bar, and that was this bar. And if you laugh, laugh, because you know, it's better laugh than being mad all the time. So let me take this out. Let me take this out, and let me take this out. Oh, the whole thing can want to collapse already because that structure is highly unstable. There you go. Now, kind of looking like the drawing over there. Okay, let's keep going. Let's keep going there. What else do we have? If you look at the joint M, you have two possibilities at the joint M. You can put a plane in the back and say, this is the joint M, so I can put a plane here in the back, and the only two will be MG and MH. Those were the only two, meaning this one must be 0. Or, once again, you can say, oh, look at that. Again, I have the same pyramid. The three of them are 0. I didn't do it like that in the video, so I'm going to continue in the way that I did it in the video. I put the plane in the back, so GM and MH fall in the same plane, meaning JM must be 0. But once I do that, what you have, what is JM here? JM is this one. I'm not gonna take that one, or yes, I'm gonna take that one. And if it breaks, it breaks. Out. Yes, out. Now look at the joint M. You can see it perfectly here. 1, 2 only. And you know, per the rule of zero force members in 2D, you have two bars only. Remember, the black bars are only there for keeping stability. That means that those two must be zero. Or you can use the pyramid thing that I said before and recognize that structure over there, and you can eliminate them as well. So let me take them out, and let me take that out. This has to go out, this has to go out, and this whole thing has to come out also. And remember, I told you this is not kind of a realistic structure. It's just for demonstration of zero force member purposes. Now this is what we have so far, and this is what we are seeing also in the PowerPoint. Do you see anything? Because I see it crystal clear. If you look at the joint now J, this is the joint J. You have only 1, 2, and 3. Pyramid again. You can eliminate the 3 of them. You have 3 in different planes and nothing else. All of them are zero force members, and you can take them out. So let me take this out from here if I can. I'm just hoping that this is not going to collapse so dramatically. It should collapse because the structure is one of the most unstable structures that I have done in my life. And take this out, hopefully. Out, yes. Now the only thing that is left here so far is that little column here with the P, with the force, which we cannot eliminate because these are collinear, these two. Even though they don't look collinear in the model, but they are collinear over there. Now, what else? What else can we do here? There's a bunch of zero force members extra here. So if you go to the joint G, well, the joint G gives you several possibilities. You can put a plane in the back, right here in the back, and when you put the plane in the back, you can see that LG, GH, and GC go in the same plane, and FG go in a different plane. So that one should be zero. Or you could also put a plane in this phase, in the first FG, in this phase, and then you could identify that GH is zero. But let's say that you didn't do that. So let's put the plane in the back like I did there, and that means that GF is going to be zero and you can take it out. But once you take it out, you look at the joint G, and you have 1, 2, 3, 2 collinear, 1 is not. That means that GH is zero as well. So let me try to take this out. It's becoming trickier by the second. Oh, I just took the F out of the joint. Now we have this, and we have that out. There you go. Out. I'm gonna keep that black bar over there just for stability. Now, what else? What else? What else? What else? Joint E. What can I identify in joint E? That's kind of difficult. Well, joint E, you could do it in several ways. Now, if you look at this force, and this force, all of the 3 forces go in the same plane, and the only thing going out of the plane will be AE. That means that that itself is a zero force members over there. That's exactly what I did there. So these 3 forces, FE, the force P, and the force EH, go in this plane, meaning AE must be a zero force member, and you take that out of there. And this is, in my opinion, the trickiest part right now. I'm gonna keep this for now here, Oh, I didn't even put the black bar for stabilizing it. So that's maybe why it's happening what is happening. But if I take this, probably I'm gonna destroy the model, so I'm gonna wait one more step. Remember, this bar doesn't exist anymore. Now, if this bar doesn't exist anymore, and you look at, there's tons of them, okay? You can move to reactions, but if let's move to reactions. I just want to follow the same procedure that I follow here. Sadly, I don't think I'm going to be able to eliminate reactions for obvious reasons, but let's try to at least. So let's say that now you go to the joint B, this joint B. If you go to the joint B and you put a plane in this face, you can see that this bar or this force, and this bar go in the same direction. That means that this reaction here, if I can take it out, please, 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 yes, is a zero force member. So Bx is a zero force member. And you could see this again, by the way. You see that theorem? If in any joint you have two collinear and one is not, the one that is not is zero, that means that this force here will be zero as well. Out. And out from there. Now, if you go to joint D, everything is the same. If you put a plane, the same approach, here, in this face, this is the joint, so I can put a plane here. The only difference between this model and the drawing is that I put the force in this side instead of the other side, but it's the same thing. If you put a plane here, you will see that this, and that are in the same, and this is in the different direction, and then you will have 1, 2 collinear, this is not, both of them are zero. So it's the same approach that we, but this is A. Well, it's gonna happen to A also. I took the wrong one. I was explaining the wrong one. I didn't take the wrong one. So if you go to the joint D, same situation. Dx is zero. Hopefully, it behaves like a zero. Out the reaction, and out the other reaction here. There you go. Out. Once you get to this point, if you see the structure, I'm gonna try to show it to you. Once you get to this point, you see this part here? This is not a pyramid. So if this is not a pyramid, you cannot eliminate that. These three fall in the same plane. If you look at this from the top also as well, this is not a pyramid where I am. Here, this is not a pyramid, and these two are not collinear. This is slanted like that. So you cannot eliminate any of these. Now, what else can we eliminate from this structure? Let's say this one here. If you look at this joint here, 1, 2, 3, this is not a pyramid, so you cannot eliminate those. There's not any rule that I can apply. And if you go to this joint, you have 1 and 1. And if you go to this joint, let's say that you put a plane in this direction, you have this and this coming out of the plane, so there's no way that you can identify anything there. And I think this is the final structure, guys. So that will be the final structure for this problem. And I hope that you like it. It's a weird structure, I'm telling you. This is extremely unstable, and this is not something that you should build no matter what, but that will help you a lot, or I hope that will help you a lot recognizing zero force members. See you next time, guys.